right, so let's start out with, we talked a little bit about this before, electrons, protons, and charge. Do we talk about what charge actually is? Well, what is charge?
Protons, electrons?
They have charge. But what is it?
It has something to do with the atom and its ability to become molecules. I'm reaching on it.
No, it's a little bit more fundamental than that. I will buy the first answer that you gave, Chase. The first thing you did was,
yeah.
all we know is that there's some property that particles seem to have that will attract or repel or not care about each other. They came up with the name charge because they realized there's three types, two of which will attract or repel, and the other one is sort of indifferent in certain situations. So, there it is. So between electrons and protons, which one has the positive charge, which one has the negative charge?
Positive proton. Negative electron.
Thereby, we get the shorthand notation of protons and electrons. What is the charge of a proton or an electron, either one? So this will be positive and that will be negative. What is the charge of a proton? There's a common answer I was expecting, but I don't know if people are silent because they know it's not the right answer or they just don't want to share.
Two.
Pardon?
Two.
Any units with that?
Not that I know of.
Well, if you aren't going with units, why not just one?
Yeah.
All right. I was expecting 1 and -1, and that is this nebulous kind of what units are there. The amount of charge for the electron is -1.6 times 10 to the -19th coulombs. And for the proton is positive 1.6 times 10 to the -19th coulombs. Now, because writing these can be sort of a nuisance. Well, first off, I have proton is equal to that. That's the charge of the proton. So we first need a symbol for charge. And the symbol for charge, as you would expect, is the letter Q. Yet one more Q because we've run out. So you might see sometimes little q, sometimes big Q. Here's a 95% rule. If you're talking about a small particle, little q. Talking about a collection of particles, big Q. So this would be a collection of charges. And this is an individual charge. Whichever Q you use, I don't care. I'll sometimes use little q, sometimes a big Q. It's just an informal convention that I've seen enough times, individual charge. So properly, this first line here is I should write that the charge of a proton is 1.6 times 10 to the -19th coulombs. And the charge of an electron is -1.6 times 10 to the -19th coulombs. That is so much to write that physicists and presumably chemists also decided to come up with a shorthand notation for that. And they said, well, why don't we just set that equal to E and this equal to -E. So the charge of an electron is -E. Now, if you've done enough math, you've run into natural logarithms and what is called the Euler's E, I think, or who's dealt with natural logarithms?
It's been a while.
Okay, so in that context, you run across this E, and that E is different from this E. That E, the one that you'll run into math class with natural logarithms and so forth, is 2.71828. So it's all based on context. We will not deal with this number in this class, not in 110. If this was 251 or 252, we would, but we're not, so we won't. All right, so what do you know about charges though? What attracts to what?
Opposites.
What do opposites do?
Attract.
They do indeed. So opposite signs attract. But if they're attracting one another, there must be a force involved. Huh. If only there were a formula for that. Oh yes, that's a look of joy back there. We are in luck. There is a formula for the force between two charges. It's going to look very similar to a formula you've seen before. First, I'm going to write down the formula you've seen before. The generalized force due to gravity. Big G, mass 1, mass 2 over r squared. That's the magnitude of the force. Let's emphasize the magnitude. The magnitude of the electric force, just the E for electric, is K Q1 Q2 over r squared. They are very similar, and that's basically where it ends, the parallel. Now, back when I was teaching in South Carolina, I had access to a proposed graduation requirements. They were going to revise South Carolina education, and one of the requirements that was in the proposal was to be able to express gravitational force in terms of electric force. Now, I mentioned this to my advisor because I found it amusing, and he did too, because not only would you graduate from a South Carolina high school, you would also win a Nobel Prize. So it did not make it into the final cut, unfortunately, because I would like to think that South Carolina had the highest standards in the country, if not the world, even though they were completely unobtainable. But physicists look at this and they see the similarities and go, there's got to be some greater connection. And some physicists spend their life trying to figure out what that connection is. If you've heard of string theory is an attempt to combine those two things, and there's a couple other theories. But string theory is too abstract for physics at the moment. In other words, we have no test for it that will differentiate it from any other theory. Now, there are two ways of approaching this. You can either play very strict adherence to the math, or you can think through the directions. So, if I have a proton here, let's make it numbers that are easier to work with. So, if I have a .31 microcoulomb charge right here, positive 31 microcoulombs. And over here, I have a negative 50 microcoulomb charge, and they are 2 meters apart. What is the force acting on? What is the force acting on the negative charge? Well, we can do a straight plug and chug. K is a constant. It has two names, because why not? It's sometimes called Coulomb's constant. Or the electrostatic constant. It is approximately equal to 9 times 10 to the 9th Newton meter squared per coulomb squared. 8.99 if you want to go another decimal point or another significant figure or two. But on the calculator, 9E9. So the force, we'll just do straight plug and chug. So I have 9 times 10 to the 9th times 31 micro. I'll leave it up to you. What's micro? It's a prefix. Okay, indeed. And let's be more specific than that. Just like milli is 10 to the negative 3rd. Nanos 10 to the negative 9th. Micro, negative 6th. Prefix. Yeah. Lowercase m, 10 to the negative 3rd. It's a mu, 10 to the negative 6th. Nano, 10 to the negative 9th. Pico, 10 to the negative 12th. Femto, 10 to the negative 15th, and that's as far as I can go in that direction. Times 50 times 10 to the negative 6th divided by the distance squared. 4. If someone would be kind enough to do that on a calculator.
Is the 50 times 10 to the negative 6, that's supposed to be a negative 50?
All right, we will get to that in a moment.
Sorry.
If you put the negative in there, I have no problem with that. This is the strict adherence to the math, or just think through it. As well as an exercise in using a calculator. You have the look of someone who has an answer.
Do you want me to round it or not round it? Round it?
Yes, sure.
I got 3.49 times 10 to
10 to the 12th.
yeah.
Something's off there. That's positive 9, negative 6, negative 6. So I know the 10 to the 12th can't be right. I don't know about the other part. Jace, you got
I
something
got
different?
something very different.
What'd you get?
I got 3.4875.
3.4875. Nothing else? No.
Nothing else. But it wouldn't be the first time I messed up with exponents.
Anyone else want to confirm or deny? Place your bets. It's as if they have just such incredible faith in you that they decided not to.
I got 3.4875.
Okay.
Same.
So it looks like this part of what KB had done is right, and it's just the exponent part. Did you figure out what the issue was?
I think I did with the negative 6 for the 50.
Ah, that could do it. All right, units. Think about what we just found. What formula do we plug into?
Newton meters over coulombs.
Coulombs?
Coulombs, yeah.
Don't forget that. No, that. You started out, but then you just kept going. Just newtons. It's force.
Okay.
In terms of this Newton meters per coulomb squared, that's just for K. Each of these is coulombs, so that would cancel out with those. And this would be a meter squared, which cancels out with that, and we're left with just newtons. All right, so it's a little over 3 newtons of force. Now, if I ask what is the force, not the magnitude of the force, but what is the force acting on the 50 microcoulomb charge, we need a direction. In which direction is the force on that negative charge?
Whatever we said. Towards the positive charge?
Towards the positive charge, yeah. We don't have much choice over that. Whether it's positive or negative,
Yeah.
we might have a choice there. So the force is in that direction, and it's 3.49 newtons. What is the force acting on the 31 microcoulomb charge?
Same thing the other way?
Yeah. Newton's third law says that they would have to be the same thing. If we had stuck the negative in there, because that was the question that Chase had asked, of should the negative be in there? If we had stuck the negative in here, then we would have ended up with a negative here. And the question is, what does that negative mean? And the negative means towards the center of the other charge. So I'm going to do a little formal notation right here. Don't let it scare you. If I took the bars off here, so that the electric force on 1 from 2, so this is the force on charge 1 from charge 2, equals K Q1 Q2 over R squared R2. This is a unit vector centered at the second charge. So if we end up with negative, that means towards the center. If it's positive, it's away from the center. And so that's the formality of it. So it's just easier just to think through, all right, opposite charges, they're attracted to each other. If I put a negative 50 microcoulomb charge there, that's 2 meters. What is the total force acting on the 31 microcoulomb charge?
3.49. Wait, repeat the question.
I have a 30 microcoulomb charge here. I have 2 negative 50 microcoulomb charges there. What is the net charge on this, on the middle one?
Like 7 newtons? Almost.
I know where you got that, and that is not correct. That is a common mistake. This is part of the thinking through it. What is the direction of the forces acting on this because of this? Which way is the force acting on the 30 microcoulomb charge from this?
Towards it.
And that's being pulled that way. I have 2 charges here. I have 2 charges pulling it in both directions.
So would it cancel each other out?
Yes, indeed. The net charges. And too many people will just plug the non-negatives in there, and the other one is negative about 7, just because they don't think through what the negative sign really means. I hope you have a wonderful break. We will all be here next Tuesday, presumably, with bells on our toes, ready to end with a flourish.